There is something alive on Mars right now. Not a signal, not a fossil buried beneath ancient red sediment, not a chemical trace left by a world that once had oceans and forgot what warmth felt like. Something alive, something that traveled there inside the belly of a machine built by human hands, launched from a pale blue world 93 million miles away, and survived every brutal condition the universe threw at it along the way. Its name is Aspergillus, and it has already beaten us to the surface. Before the first boot print ever marks Martian soil, before the first pressurized dome catches the dim light of a sun that looks, from that distance, like nothing more than a very bright star, before any of that, a microscopic organism born in the dust and decay of Earth has already made the crossing. Quiet, patient, invisible to the naked eye, smaller than the period at the end of this sentence, and yet more resilient than anything our most advanced engineering has ever produced. We sent rovers to look for life on Mars. We may have sent life to Mars on the rovers. This is not a theory. This is not speculation dressed in the language of science fiction. This is a documented, peer-reviewed, NASA-acknowledged reality in the clean rooms where spacecraft are built. Rooms where the air is filtered hundreds of times per hour, where technicians wear full-body suits and breathe through filtered masks, where every surface is bathed in ultraviolet light and scrubbed with chemicals that would strip paint from steel. Aspergillus niger, Aspergillus fumigatus, and their closest kin were found alive, found clinging to surfaces that had already been sterilized, found in cultures taken from the walls of facilities designed with one singular purpose: to keep exactly this from happening. NASA's own bioburden reduction program, a meticulous global effort to prevent the forward contamination of other worlds, identified this fungus repeatedly. It survived the cleaning. It survived the irradiation. It endured conditions that would reduce most Earth life to nothing but molecular wreckage. Now consider what it survived after that. The launch, the violent hammer of a rocket engine burning 3 million pounds of thrust, shaking the airframe with forces that would liquefy human bone. The vacuum of deep space, where pressure drops to near zero and unfiltered solar radiation tears through organic material like light through wet paper. Temperature swings of more than 300 degrees between the sunlit hull and the shadowed side of the spacecraft. Months of transit, a brutal atmospheric entry, and then Mars, a world with a surface pressure less than 1% of Earth's, bathed in ultraviolet radiation because it has no magnetic field and almost no ozone, with an average temperature of negative 80 degrees Fahrenheit. Aspergillus has survived all of it, not in theory, in practice, in controlled laboratory simulations conducted specifically to understand what would happen if a fungal spore hitchhiked on a spacecraft. The results were unambiguous. The spore endured. It waited, and given the right chemical cues, the faintest trace of moisture, the presence of organic carbon, conditions that on Mars are not impossible, it can germinate. Life, as it turns out, did not need our permission to go interplanetary. It just needed a ride. And we gave it one. What makes Aspergillus extraordinary is not that it survives. Survival, in isolation, is a common story in biology. Bacteria endure boiling vents beneath the ocean floor. Microbes sleep for millennia trapped in ice. Tardigrades collapse into cryptobiotic husks and wait out the vacuum of space as if time itself had paused. But Aspergillus does something more unsettling. It thrives in the margins where survival should end. It belongs to a vast kingdom of fungi, organisms that do not move, do not hunt, do not think in any way we recognize, and yet quietly reshape entire worlds. Fungi are the great recyclers of Earth. They digest what nothing else can. Stone, plastic, radiation-altered debris. The aftermath of catastrophe becomes their nourishment. Where life collapses, fungi begin their work. Aspergillus is one of their most adaptable emissaries. Its spores are microscopic capsules of persistence, engineered by evolution to endure extremes that resemble the hostile silence of space itself. Each spore is a sealed vessel, containing the bare minimum required for life to restart. Not active, not growing, not even fully alive in the way we typically define it. It exists in suspension, in a state that blurs the boundary between life and inert matter. It waits. And waiting in the universe is a form of power. Because the universe is not hostile in a constant way. It is hostile in waves, bursts of radiation, violent fluctuations in temperature, long stretches of emptiness punctuated by moments of fleeting opportunity. A passing comet releases water vapor. A thin layer of frost forms on a Martian rock at dawn. A microscopic pocket of brine persists beneath the surface, shielded from ultraviolet light. To most forms of life, these moments are too brief, too weak, too rare. To Aspergillus, they are enough. In laboratory simulations designed to replicate Martian conditions, spores of Aspergillus niger were exposed to ultraviolet radiation levels comparable to the unfiltered surface of Mars. Radiation that shreds DNA, breaks chemical bonds, and erases the molecular instructions that define life. Within minutes, most organisms would be reduced to biological noise. Yet a fraction of these spores remained viable, not untouched, not unchanged, but intact enough to repair themselves. Because within each spore lies not just a blueprint for life, but a toolkit for recovery. DNA repair mechanisms activate when conditions stabilize. Protective pigments absorb and dissipate radiation energy. The cell wall itself acts like a shield, layered and dense, reducing the penetration of destructive forces. It is not invincible. It is persistent. And persistence, over long enough timescales, begins to resemble inevitability. Consider the journey from Earth to Mars. It is not a straight path, but a slow, arcing transfer through a region of space flooded with cosmic rays. High-energy particles born from distant supernovae streak across the solar system, passing effortlessly through metal hulls and living tissue alike. Each impact is a microscopic explosion, capable of fracturing DNA strands. A human exposed to this environment without shielding would suffer irreversible damage within days. A fungal spore does not panic. It does not resist in the way an organism with a nervous system might. It simply accumulates damage and waits, because its strategy is not to remain perfect. Its strategy is to remain possible. This is the subtle genius of its design. Life, at its core, is often imagined as something fragile. A delicate balance of chemistry that collapses under stress. But Aspergillus reveals a different philosophy. Life can be rugged, redundant, prepared to break and rebuild itself repeatedly, as many times as necessary, until conditions align once more with growth. It does not need comfort. It needs opportunity. And Mars, despite its desolation, is not entirely devoid of opportunity. Beneath its oxidized surface, there are salts that can attract and hold water molecules, forming transient brines. These liquids are not like the rivers and oceans of Earth. They are cold, chemically aggressive, and ephemeral. But they exist for minutes, for hours, sometimes longer beneath the surface, where radiation cannot easily reach. In those fleeting windows, the impossible becomes merely unlikely, and unlikely, given enough time, becomes inevitable. This is where the story begins to shift from biology to philosophy. Because the presence of Aspergillus on Mars forces a question that is both scientific and existential in equal measure. What does it mean to contaminate another world? For decades, planetary protection has been treated as a technical problem. Clean the spacecraft, reduce microbial load, monitor contamination levels, establish thresholds that define what is acceptable and what is not. It is a system built on measurement and control. But control, in this context, is an illusion measured in degrees, not absolutes. Because even a single surviving spore is not zero. And zero is the only number that guarantees sterility. When a spacecraft leaves Earth, it carries with it more than instruments and cameras. It carries a shadow of the biosphere that built it. Invisible hitchhikers embedded in microscopic crevices, shielded by layers of material, protected by the very complexity of the machines designed to explore the cosmos. We build spacecraft to withstand extremes: vacuum, radiation, temperature, mechanical stress. In doing so, we inadvertently create environments that also protect the smallest forms of life we are trying to exclude. It is a paradox. The more resilient our technology becomes, the more capable it is of preserving the resilience of biology. And so, without intention, we become agents of distribution, not conquerors of worlds, but vectors, carriers. The distinction matters, because if Aspergillus can survive the journey to Mars, then Mars is no longer an isolated system in the way we once imagined. It becomes part of a biological continuum, connected not by natural processes alone, but by the deliberate actions of an intelligent species that did not fully anticipate the consequences of its reach. There is a quiet irony here. Humanity has spent centuries asking whether we are alone in the universe, building telescopes to search for distant biosignatures, sending probes to drill into alien soil, searching for chemical whispers of life that may have existed billions of years ago. And in that search, we may have already altered the answer. If a future mission detects fungal growth beneath the Martian surface, how will we know if it is truly Martian? How will we distinguish between life that emerged independently on another world and life that originated here on Earth and simply endured the journey outward? The question becomes even more complex when we consider time, because contamination is not a single event. It is a process, slow, cumulative, and often invisible until it reaches a threshold where its effects can no longer be ignored. A spore today, a colony decades from now, a microscopic ecosystem centuries into the future. Mars changes, not dramatically, not in ways that transform it into a second Earth, but in subtle, irreversible ways that blur the boundary between native and foreign. And all of it begins at a scale so small, it escapes direct perception. A single spore, resting on a surface of red dust, beneath a sky the color of rust, waiting for a moment of liquid water that may last only minutes. Minutes are enough, because life does not measure time the way we do. For a human, minutes are fleeting. For a fungal spore that can remain dormant for years, decades, even longer, minutes are an opportunity as significant as a season. And so it waits, as it always has, not with intent, not with awareness, but with a kind of quiet inevitability encoded in its structure. The universe does not need life to be intelligent to be persistent. It only needs it to endure. And Aspergillus endures in a way that forces us to confront an uncomfortable truth. We are not just explorers of the cosmos. We are participants in its biological transformation, whether we intended to be or not. Mars was not always the silent, frozen desert we see today. There was a time when liquid water moved across its surface with intention. Valleys carved themselves into the crust like slow signatures written by rivers that refused to remain still. Minerals formed in the presence of persistent moisture. The chemistry of the soil remembers this past, even if the planet itself no longer expresses it openly. To understand what Aspergillus represents on Mars, it is necessary to imagine not only what Mars is, but what it was, and what fragments of that past still remain hidden beneath its surface. Because life does not require a planet to be alive in the way Earth is alive. It requires gradients, energy differences, chemical imbalances waiting to be resolved. Life emerges where the universe is not in equilibrium, where something can flow, react, and reorganize itself into patterns that sustain their own existence. Mars, even in its current state, is not entirely at rest. Beneath the oxidized dust that gives the planet its characteristic red hue lies a chemically reactive environment. Perchlorates, highly oxidizing salts, are scattered throughout the soil. To most Earth organisms, these compounds are toxic, disruptive to cellular processes, corrosive to the fragile machinery of life. But for certain extremophiles, including some fungal species, toxicity is not a barrier. It is a condition to be adapted to. On Earth, there are organisms that metabolize compounds once thought universally lethal. They use them as energy sources, transforming chemical hostility into biological opportunity. The boundary between poison and nourishment becomes a matter of perspective, shaped by evolution over immense timescales. Aspergillus does not yet metabolize perchlorates in the same way specialized bacteria do, but it possesses a metabolic flexibility that allows it to endure chemically aggressive environments long enough to exploit moments of reduced hostility. It can enter dormancy when conditions are unfavorable and reactivate when the environment briefly shifts. Mars provides those shifts. At certain latitudes and times of year, temperature fluctuations allow for the formation of thin films of liquid brine. These are not stable bodies of water, but transient layers that appear and disappear like breath on cold glass. Invisible at a distance, fleeting even under close observation, but chemically real. For a fungal spore, this is not a limitation. It is a signal. The presence of liquid, however temporary, allows for molecular movement. Nutrients can dissolve. Enzymatic reactions can begin. The rigid stillness of dormancy can soften into the first stages of activity. Hyphae, the filamentous structures that define fungal growth, can begin to extend, probing the surrounding environment in search of resources. Growth does not need to be rapid. It only needs to begin. And once it begins, it leaves traces. Microscopic alterations to the surrounding material. Chemical gradients shifted by metabolic activity. Organic compounds produced and deposited into the environment. These are the fingerprints of life, subtle but persistent. Now consider the implications for planetary exploration. When instruments are sent to Mars to search for biosignatures, they are designed to detect precisely these kinds of changes. Organic molecules, patterns in isotopic ratios, structures that suggest biological processing rather than purely abiotic chemistry. But if Aspergillus, or any terrestrial microorganism, has already begun to interact with the Martian environment, even at the smallest scale. Then the data we collect becomes entangled with our own presence. The signal is no longer clean. It becomes a conversation between two worlds, one indigenous and one introduced. And the instruments we rely on cannot easily distinguish between the two if their chemical signatures overlap. This is not a failure of technology. It is a reflection of how similar life can be, even across radically different environments. Because all life we know shares a common origin. It is built from the same molecular alphabet: DNA, RNA, proteins, lipids. Variations on a single theme that began on Earth billions of years ago. If life ever existed on Mars independently, it may have followed a different biochemical path, or it may have converged on similar solutions, shaped by the same physical laws that govern chemistry throughout the universe. We do not know. And that uncertainty is where contamination becomes more than a technical problem. It becomes a philosophical boundary. Because once Earth life is present on Mars, even in trace amounts, the question, "Is there life on Mars?" transforms into something more complex. It becomes, which life are we detecting? And beyond that, did we erase the answer before we could fully understand the question? There is another layer to this, one that extends beyond detection and into transformation. Fungi are not passive inhabitants of their environments. They are engineers, albeit on a microscopic scale. They secrete enzymes that break down complex materials. They alter the chemical composition of their surroundings. Over time, they can contribute to processes that change the structure of entire ecosystems. On Earth, fungi played a crucial role in the transition of life from water to land. They formed symbiotic relationships with early plants, helping them extract nutrients from barren rock. They participated in the gradual transformation of sterile landscapes into habitable environments. This process took millions of years. But it began with small, incremental steps. Now imagine a similar process, not driven by natural evolution on Mars, but initiated by organisms from Earth. Aspergillus, given enough time and the right conditions, could begin to interact with Martian regolith in ways that alter its chemistry. It could contribute to the breakdown of minerals, the redistribution of elements, the slow accumulation of organic matter. Individually, these changes are negligible. Collectively, over long timescales, they become significant. Mars would not suddenly bloom with forests or oceans, but it would no longer be entirely untouched. It would carry a trace of Earth's biology embedded within its soil, a quiet imprint of a distant world that reached across space and left something behind. This raises a question that does not have a simple answer. Do we have the right to do this? Not in a legal sense, but in a cosmic one. Mars has existed for billions of years as an independent system. Its history, its chemistry, its potential for past or present life, all of it developed without influence from Earth. It is, in every meaningful way, a separate chapter in the story of the solar system. And yet, in the span of a few decades, we have begun to blur that separation, not through intention, but through inevitability. Because the act of exploration carries with it a form of contact. Even when that contact is unintended, even when it occurs at scales too small to observe directly, it is still real. It changes the system. And once changed, it cannot be returned to its original state. There is no reset. This is the deeper implication of Aspergillus on Mars. It is not just a resilient organism surviving in an extreme environment. It is a symbol of a transition, a shift from a solar system where planets were isolated, evolving independently, to one where at least one species, ours, has begun to connect them, not only with machines and signals, but with life itself. We often imagine the spread of life beyond Earth as something deliberate. Terraforming, colonization, the careful introduction of ecosystems designed to transform other worlds into habitable environments. But the reality may be far more subtle. It may begin not with grand projects, but with contamination. With spores too small to see, carried unintentionally across millions of miles, surviving against expectations, and waiting for moments that are almost too brief to matter. Almost. Because in the universe, almost is often enough. And once life gains a foothold, however small, it begins to participate in the ongoing process of change. Mars, in this sense, is no longer entirely Mars. It is becoming something else, something influenced, however slightly, by a world that orbits a different star's light, that breathes a different atmosphere, that evolved life under entirely different conditions. A convergence has begun, slow, quiet, invisible, but real. And Aspergillus is one of its first messengers. If the story ended with survival, it would already be remarkable. But survival is only the first chapter. The deeper question is what happens next. Because Aspergillus is not merely a passenger that endures hostile conditions. It is a system capable of interaction, adaptation, and, under the right circumstances, transformation. Its true significance lies not in the fact that it can reach Mars, but in what it might do once it is there, embedded within an environment that is alien, yet not entirely incompatible with the fundamental logic of life. To understand this, it is necessary to look closer at the architecture of the organism itself. A fungal colony does not grow like a plant or move like an animal. It expands as a network, a branching web of microscopic filaments known as hyphae. These filaments extend outward in all directions, probing the environment with a kind of chemical sensitivity that replaces sight, sound, and touch. Each tip is both a sensor and a tool, capable of detecting gradients in nutrients, moisture, and chemical composition. Growth is not random. It is guided by invisible landscapes of possibility. On Earth, this network can infiltrate soil, penetrate rock, and even colonize synthetic materials. There are documented cases of fungi growing on the surfaces of spacecraft components, feeding on trace organic residues, adhesives, and even certain types of polymers. Materials we consider inert are, to a fungus, potential sources of energy waiting to be unlocked through biochemical persistence. Now place that capability on Mars. The Martian regolith is not biologically active in the way soil on Earth is, but it is not inert. It contains iron oxides, silicates, sulfates, and perchlorates, compounds that, under specific conditions, can participate in chemical reactions that release or redistribute energy. A fungal network interacting with this environment would not behave as it does on Earth, but it would not be entirely without options. It would explore, slowly, almost imperceptibly. Hyphae would extend into microscopic crevices between grains of dust. They would encounter a landscape defined not by abundance, but by scarcity. Each extension would be a calculation, encoded not in thought, but in biochemical feedback. Where moisture is absent, growth halts. Where a trace of water persists, growth continues. Where radiation has damaged cellular structures, repair mechanisms engage, or the affected segment is abandoned. This is not efficiency as humans define it. It is resilience expressed spatially. a fungal network does not need every part of itself to survive. It only needs enough of itself to persist and expand when conditions allow. Portions can die while others continue, creating a patchwork existence that mirrors the fragmented, intermittent habitability of Mars itself. There is a strange symmetry here. Mars offers fleeting opportunities for life. Aspergillus offers a form of life designed to exploit fleeting opportunities. The match is not perfect, but it is not impossible. Over time, even minimal activity can accumulate into measurable change. Fungi produce organic acids as part of their metabolic processes. These acids can interact with minerals, altering their structure, dissolving certain components, and releasing others. On Earth, this contributes to soil formation and nutrient cycling. On Mars, the same processes would occur at a vastly reduced rate. But the principle remains the same. Chemistry would shift, not dramatically, not in ways visible from orbit, but at the scale where life operates. Microns, molecules, gradients, there would be movement. A static environment would become slightly less static. And where there is movement, there is the potential for feedback. This is where the concept of ecological succession, familiar on Earth, takes on a new and unsettling dimension. On our planet, ecosystems often begin with pioneer species, organisms capable of colonizing barren environments. These pioneers alter the landscape, making it more suitable for other forms of life to follow. Over time, complexity increases. Diversity emerges. What was once sterile becomes alive. Now imagine that process beginning, however faintly, on Mars, not as a natural evolution of Martian life, but as a consequence of terrestrial organisms adapting to an alien world. Aspergillus would not transform Mars into Earth, but it could initiate processes that make Mars slightly less hostile to other Earth-derived microbes. Organic material produced by fungal metabolism could serve as a substrate for bacteria. Chemical alterations to the regolith could create microenvironments where additional reactions become possible. A cascade, slow and fragile, but real. This is how ecosystems begin, not with abundance, but with persistence. The philosophical weight of this is difficult to ignore, because it suggests that life, once introduced to a new environment, does not remain static. It participates, it modifies, it creates conditions that can amplify its own presence, even if only marginally. And this leads to a question that extends beyond Mars. If we can inadvertently seed life on a neighboring planet, what happens as we move further into the solar system? To the icy moons of Jupiter and Saturn, where subsurface oceans exist beneath thick shells of ice. To environments that may already harbor their own forms of life, adapted to conditions entirely different from those of Earth. Europa, Enceladus, worlds where liquid water exists in darkness, heated by tidal forces rather than sunlight. Environments isolated for billions of years, potentially hosting ecosystems that have never interacted with the biology of Earth. The introduction of terrestrial organisms into such systems would not be a simple contamination. It would be an intrusion into a separate evolutionary experiment. And once that intrusion occurs, it cannot be undone. This is why planetary protection exists, not merely as a technical discipline, but as an ethical framework. It is an acknowledgement that exploration carries consequences that extend beyond data collection and discovery. It is an acknowledgement that we are not neutral observers. We are participants. Aspergillus forces this realization into focus because it operates below the threshold of our perception. It does not announce its presence. It does not require large-scale failures or dramatic breaches of protocol to spread. It exploits the smallest imperfections, the tiniest lapses, the unavoidable realities of working with physical systems in a non-sterile universe. Absolute sterility is a theoretical ideal. In practice, it is asymptotic. We approach it, but we never reach it. And in that gap between intention and reality, life finds its way. There is also a more intimate dimension to this story. Aspergillus fumigatus, one of the species identified in spacecraft assembly environments, is not just an extremophile, it is also an opportunistic pathogen. In humans with compromised immune systems, it can cause severe infections, invading lung tissue and spreading through the bloodstream. On Earth, this dual identity is well understood. It is both a common environmental organism and a potential threat under specific conditions. Now consider its presence in the context of future human missions to Mars. Habitats will be closed systems. Air will be recycled. Resources will be limited. The balance between sterility and sustainability will be delicate. Completely eliminating all microorganisms is neither practical nor desirable, as human health depends on complex microbial ecosystems. But the introduction or persistence of resilient fungi in such environments introduces risk. Spores could accumulate in air filtration systems, colonize surfaces, or interact with materials in ways that degrade infrastructure over time. Fungi are known to contribute to biocorrosion, breaking down metals, plastics, and composites through chemical processes that operate slowly but persistently. In the confined environment of a Martian habitat, these processes would not be abstract. They would be operational challenges. Maintenance would become a constant negotiation with biology. Systems designed to support life would also need to resist it. The boundary between habitat and ecosystem would blur, as microscopic organisms find ways to persist within the very structures meant to exclude them. This is the paradox of carrying Earth with us. We do not travel alone. We bring with us an entire biosphere, scaled down, filtered, controlled, but never entirely absent. And among its countless members are organisms like Aspergillus, which do not require our awareness to accompany us. They are already part of the journey, already part of the equation. And perhaps, in ways we are only beginning to understand, already part of the future of life beyond Earth. There is a tendency to imagine contamination as a failure, a breach, a mistake, a deviation from a protocol that, if perfectly followed, would preserve the purity of distant worlds. It is a comforting narrative because it suggests control. It implies that with enough precision, enough discipline, enough technological refinement, we can separate ourselves from the environments we explore. But Aspergillus does not exist within that narrative. It reveals something more fundamental. Contamination is not always an error. Sometimes it is a consequence, because every object we build carries a history. Every surface, no matter how polished, no matter how sterilized, is part of a chain of interactions that began long before it was assembled into a spacecraft. Materials are extracted from Earth, processed, handled, exposed to air, to microscopic particles, to the constant invisible exchange between organisms and their environment. Sterilization reduces this history. It does not erase it. And in that residual trace, life persists. The concept of a clean room is, in many ways, a negotiation with this reality. Air is filtered to remove particles down to fractions of a micron. Surfaces are treated with chemical agents designed to disrupt cellular structures. Ultraviolet radiation is used to damage DNA, preventing replication. Each layer of protection narrows the window of survival, but it never closes it completely. Because Aspergillus operates at the edge of what these measures can achieve, its spores are not simply small. They are structured for endurance. The outer layers contain pigments such as melanin, which absorb and dissipate radiation, acting as a kind of biological armor. The internal environment is dehydrated, reducing the likelihood of chemical reactions that would otherwise damage critical molecules. Metabolic activity is nearly halted, minimizing the vulnerability that comes with being alive in an active sense. It is, in effect, a system designed to outlast attempts at its own elimination, not deliberately, but inevitably, through the logic of evolution. Over billions of years, organisms that could endure extreme conditions were selected for survival in environments where others could not persist. Radiation, desiccation, temperature extremes. These are not unique to space. They exist in deserts, in high-altitude regions, in the upper atmosphere, in niches where life is pushed to its limits. Space is not entirely foreign to life. It is an extension of extremes already present on Earth. This is why certain organisms can survive exposure to it, not because they were meant to, but because they were prepared by entirely different pressures. Aspergillus did not evolve to survive a journey to Mars. It evolved to survive unpredictability. And unpredictability is one of the defining characteristics of the universe. This leads to a realization that reframes the entire concept of planetary isolation. We often think of planets as separate systems, each with its own boundary defined by gravity, atmosphere, and distance. Earth is here. Mars is there. The space between them is vast, empty, and acts as a barrier. But life does not necessarily perceive that barrier in the same way. For a human, the journey to Mars is an immense undertaking, requiring complex engineering, precise calculations, and enormous energy. For a spore, the journey is passive. It does not navigate. It does not choose. It endures. And endurance transforms distance. The vacuum of space, the radiation, the cold. These are filters, not absolute barriers. They reduce the number of organisms that can make the crossing, but they do not reduce it to zero. And again, zero is the only number that guarantees isolation. Anything above zero introduces possibility. This is not limited to human-made spacecraft. Meteorite exchange between planets has occurred throughout the history of the solar system. Rocks ejected from the surface of Mars by impact events have been found on Earth. Some of these rocks experienced conditions during ejection and transit that, while extreme, may not have been entirely sterilizing. This raises the concept of lithopanspermia, the idea that life can be transferred between planets via natural processes. If that is possible, then the presence of Aspergillus on Mars is not an entirely unprecedented event. It is an acceleration, a directed version of a process that may already occur, but at much lower probabilities and over much longer timescales. Human activity compresses time. What might happen once in millions of years through random events can now happen within decades through deliberate exploration. We become catalysts, not creators of the process, but amplifiers. And amplification changes outcomes. A rare event becomes more common. A possibility becomes a likelihood. And over time, likelihood becomes expectation. This has profound implications for how we understand life in the universe. If life can move between planets, whether through natural processes or technological ones, then the distribution of life may not be as isolated as once assumed. pockets of biology could be connected, not continuously, but intermittently, through rare transfers that seed new environments with familiar chemistry. In such a universe, discovering life elsewhere does not automatically mean discovering an independent origin. It could mean encountering a distant relative, a branch of the same tree, carried across space and given the opportunity to grow under different conditions. Aspergillus, in this context, is both a warning and a clue. A warning because it demonstrates how easily we can interfere with environments we seek to study in their pristine state. A clue because it reveals the mechanisms by which life might naturally disperse, even without intention. It occupies the intersection between contamination and panspermia, between accident and inevitability. And in doing so, it challenges a deeply rooted assumption that life belongs where it originates. Perhaps it does not. Perhaps life, once it emerges, has a tendency to spread, to explore, to occupy any niche that can support it, no matter how briefly or how marginally. Not through conscious expansion, but through the cumulative effect of countless small events. A spore lifted into the atmosphere, a particle embedded in a spacecraft, a fragment of rock ejected by an impact. Each event, on its own, is insignificant. Together, they form a network of possibilities that extends across space. This perspective shifts the role of humanity in a subtle but important way. We are not introducing something entirely new to the cosmos. We are participating in a process that may already exist, but we are doing so with unprecedented speed and scale, and without fully understanding the consequences. Because the consequences are not immediate. They unfold over timescales that exceed individual human lives, often exceeding entire civilizations. The contamination of Mars, if it occurs in a meaningful way, will not be fully realized in years or decades. It will be a slow transformation, measured in centuries, perhaps millennia. By the time its effects are clear, the context in which the initial actions were taken may be long forgotten. This is the nature of long-term processes. They disconnect cause from effect. They obscure responsibility. And yet, they remain the direct result of actions taken at specific moments in time, moments like this one, where a species stands at the threshold of becoming interplanetary, not just in presence, but in influence. Aspergillus is a reminder that influence does not require intention. It does not require awareness. It only requires interaction. And once interaction begins, it cannot be undone. The universe keeps a record, not in memory, but in change. Every altered surface, every shifted chemical balance, every organism that survives where it was not before. These are the entries in that record. Mars is beginning to accumulate them, quietly, invisibly, but persistently. And somewhere, perhaps beneath a thin layer of dust, shielded from the harshest radiation, a spore waits. Not as an invader, not as a conqueror, but as a possibility. A possibility that carries within it the entire history of life on Earth, compressed into a structure too small to see, yet complex enough to endure the journey between worlds. A possibility that asks a question without words. What happens when life refuses to stay where it began? In the end, the question is not whether Aspergillus can survive on Mars. It already has. The deeper question is what that survival means for us. Because in that microscopic act of endurance, silent, unobserved, almost insignificant, there is a reflection of something far larger than a single organism, or even a single planet. There is a reflection of life itself, and of the role we now play in its unfolding story. For most of Earth's history, life was bound to this world by forces it could not overcome. Gravity held it close. The atmosphere sheltered and confined it. The vacuum beyond was an absolute barrier, as unreachable as the depths of time. And yet, through us, that barrier has been crossed, not by evolution alone, but by intention layered on top of evolution, by intelligence emerging from biology, and then turning outward, building machines that extend the reach of life beyond its place of origin. We often describe space exploration as a human endeavor, but it is more accurate to say that it is a biological event, because every spacecraft we launch is, in some measure, an extension of Earth's biosphere, not just metaphorically, but physically, carrying with it fragments of the planet's chemistry, its materials, its microorganisms, its history. We do not leave Earth behind. We carry it with us. And in doing so, we blur a boundary that once seemed absolute. Mars, for billions of years, existed as a separate chapter in the story of the solar system, a world that diverged from Earth early in its history, losing its magnetic field, its thick atmosphere, its surface water. A world that became cold, dry, and exposed to radiation. A place where life, if it ever existed, would have been forced into hiding or erased entirely. It was, in a very real sense, alone. Now, that aloneness is beginning to erode, not through dramatic transformation, but through the quiet introduction of possibility. A spore here, a microbe there, each one a thread connecting two worlds that were once entirely separate. These threads are fragile. Most will break, most will lead nowhere. But some may hold. And over time, even a few connections are enough to change the structure of the system they link. This is how networks form, not all at once, but gradually, through repeated interactions that accumulate into something more complex than their individual parts. If life takes hold on Mars, even at the smallest scale, it becomes part of that network. A node in a system that now spans at least 2 planets, connected not by continuous flow, but by intermittent transfer and persistence. It is a subtle beginning, but beginnings often are. There is a temptation to view this as contamination in the most negative sense, as a loss of purity, as the irreversible alteration of a world we sought to study in its untouched state. And that perspective is not wrong. There is value in preserving environments as they are, in understanding them before we change them. There is a scientific clarity that comes from isolation, from knowing that what we observe has not been influenced by external factors. But there is another perspective, one that is less about preservation and more about continuity. Life on Earth has never been static. It has spread, adapted, transformed every environment it has encountered, from the depths of the oceans to the upper atmosphere, from volcanic rock to frozen ice. It has expanded into every niche that could support it, however marginally. Expansion is not a decision life makes. It is a property of life itself. Given the opportunity, it fills available space. And now, for the first time in billions of years, the available space has expanded beyond a single planet. The question is not whether life will move into that space. It is whether we will understand the consequences of that movement. Because with awareness comes responsibility, not the responsibility to prevent all change that may be impossible, but the responsibility to recognize that change is occurring and that we are part of it. Aspergillus does not carry intention. It does not choose to travel to Mars. It does not consider the ethical implications of its presence there. But we do. Or at least, we have the capacity to. This is what distinguishes our role in this process. We are not just carriers. We are observers who can become participants with foresight. And foresight introduces a new dimension to exploration. It transforms it from a purely technical challenge into a philosophical one. What kind of presence do we want to have in the cosmos? Do we move outward carelessly, accepting contamination as an inevitable byproduct of progress? Do we attempt to impose strict controls, knowing they will never be perfect? Do we embrace the spread of life as a natural extension of its history? Or do we treat other worlds as places to be protected from the very biology that defines us? There is no simple answer. Because each path carries trade-offs. Preservation may limit exploration. Exploration may compromise preservation. And somewhere between these extremes lies a balance that has yet to be fully defined. Mars is the first testing ground for this balance. Close enough to reach, hostile enough to challenge us, similar enough to Earth to tempt the idea that it could one day support life again, whether native or introduced. And already, before any human has set foot on its surface, the question is no longer theoretical. It is real, because life from Earth is already there, quietly, persistently, waiting. There is a final, deeper implication to all of this, one that extends beyond Mars, beyond the solar system, and into the broader question of life in the universe. If life can survive the journey between worlds, even in its simplest forms, then the universe may not be as biologically isolated as it appears. The distances between stars are vast, but so are the timescales over which processes can unfold. Given enough time, enough events, enough persistence, the seeds of life could move. Not frequently, not easily, but not impossibly. In such a universe, life is not confined to the places where it begins. It becomes something that can, under the right conditions, propagate across the void, slowly, sporadically, but inevitably. Aspergillus is not proof of this on a cosmic scale, but it is a demonstration of the principle. A single organism, evolved on Earth, surviving conditions that resemble the space between worlds, enduring a journey to another planet, and retaining the capacity to become active once it arrives. It is a small thing, but small things, repeated across vast scales of time and space, can reshape entire systems. This is how stars form, how galaxies evolve, how life itself emerged from chemistry, not through singular events of overwhelming magnitude, but through the accumulation of countless small possibilities that together become reality. And now, we are part of that accumulation, not as passive observers, but as active contributors. Every mission we launch, every surface we touch, every organism that travels with us, seen or unseen, all of it becomes part of the ongoing story of life extending beyond its origin. Mars is no longer just a destination. It is a beginning, a place where the boundary between worlds has already been crossed, not with footsteps, but with something far smaller and perhaps far more enduring. A spore, drifting through the cold silence of space, surviving the impossible, arriving without announcement, and waiting, as it always has, for the universe to offer it a moment. Because a moment is all it needs, and the universe, patient and vast, always provides.